So we had that triangle. I kind of got you started with it a little bit. I posted a video yesterday related to magnitude of the cross product. It's one of those things where it just kind of boiled down to if you like it, go for it. If you don't like it, then don't bother with it. Let me see if I can pull it up real quick. Actually, let me pause the video so I can find it. So resume recording. I leave it up to you which way you want to go, assuming that anything wants to work tonight, for crying out loud. Oh, preparing my library for a faster experience by knocking me out of my library. That's wonderful. All right, so anyway, the setup here was to find 1/2 of the cross product between PR and PQ. All right, so what I'll do is I'll just kind of tuck these away for the time being. I'll just kind of shrink them down. Put them in the corner. We need to find PR. All right, so that's the difference between corresponding values in P to R. So 0 minus 1 is -1, 0 minus 0, and then 1 minus 0. So 0, 1. All right, and PQ, 0 minus 1, -1, 1 minus 0 is 1, and then 0 minus 0 is 0. Right, so we have those values there. Now it's a matter of, just pick your poison. I look at the first one as being not too difficult when you compare it to the others, because in the other cases, you have to do something additional, right? Here, you would just find the magnitudes and then also the dot product, which is not difficult. So I'd be looking at, so let's say I wanted to use my brand newfangled technique. I'd be looking at the magnitude of PQ, which is the square root of the squared values. So we're talking about 1 plus 0 plus 1. So under a radical is going to be radical 2. Then PR, well, actually, that should have been PR. So PR is radical 2. It turns out the PQ is going to be radical 2 anyway, but for consistency. Right, so -1 squared is 1, 1 squared is 1, 0 squared is 0. Add them up, I get a radical 2. And I get a 2, but under a radical. Right, so then I'd be looking at each of those values squared, which I'll get to in a minute, but PR dotted against PQ. So I'm multiplying corresponding values and adding them together. I'm going to get 1 plus 0 plus 0 is going to give me a 1. All right, so if I want to use my handy dandy newfound formula, which allows you to avoid the trig, the complications of the trig, I'm taking each of these values and squaring them. So 2 times 2 minus then my dot product squared, which is 1 squared or just 1. Ooh, that's fun looking. And so we would get radical 3. All right, so that would be the magnitude of the cross product between those two vectors. All right, that gives you the area of the entire parallelogram. I don't want the whole parallelogram, I only want half of it. So the area of the triangle would be 1/2, again, of the magnitude PR crossed against PQ, which would be 1/2 times radical 3, or radical 3 over 2 square units. I'll just say units squared. All right, so a little bit more crunching of the numbers, but not too crazy, I don't think, anyhow. So hopefully you found that to be beneficial. If you want to see where that formula came from, then definitely check out the video I posted in the playlist on YouTube. And of course, make sure you drop a like on it to show your support. Click that bell icon for notifications, etc. So, yeah, just a thought. The fallback is to find the cross product between the two vectors and then find the magnitude, which is not going to be too crazy if you just need the number, because you just crank it out by hand. With these cases, it's lots of zeros and ones, so it's fine. Or you can pop it in GeoGebra, in which case, you're going to get it even quicker. So you should be all right. So we're up to the triple scalar product, which sounds really fancy. It's we're talking about, in that case, determinant of a 3x3 matrix. I'm going to show you the concept of vector operations using Desmos, just so we can kind of streamline that. I kind of went a little video crazy over the weekend. One of the videos that I showed or posted involved row reduction techniques, reduced row echelon form for solving linear systems, because there's no reason why we should have to get bogged down with the basic algebra when all we need is a solution to a linear system. Right? The determinant is along the same lines, where it's like we could do it by hand, but then it's more of a linear algebra course. There will be elements of crossover between this class and linear algebra, but we don't want it to be like, okay, well, we just wasted half of our class learning about linear algebra. Now we can do like 5 minutes of Calc 3. I don't want it to be like that. And it's already in danger. The course anyway is in danger of becoming like that. So I want to try to kind of scale it down as much as possible. That's where technology comes into play. All right. So what we get is the triple scalar product, which gives us the determinant of a 3x3 square matrix, which is equivalent to dotting U against the cross of V and W. All right. So it's kind of weird when you think about it, but it'll make all the sense in the world when we get into the practical application. So let's flip the page and actually get into the skill, and then we'll talk applications. All right. So if we're looking for the triple scalar product, all we're going to do is create a 3x3 square matrix from the vectors U, V, and W. Right. And then we're going to find the determinant of that. So we're looking for U dotted against V crossed against W. So all because I don't want to use the line draw tool anymore. So 1, 3, 5, 2, -1, 0, -3, 0, -1. So we're using row vectors instead of column vectors, and that's fine. They're conceptually equivalent in the context that we're using them. So if you're familiar, when you think of linear algebra concepts, if you're more familiar with writing vectors in column form, that's fine. The way we're treating them, they mean the same thing. All right, we're just working with the transpose, if you know what that means, of those column vectors into row vector form. Okay. So what I need is the determinant of this. So what I'm going to do is I am going to go to my handy dandy Desmos matrix calculator. All right, might have skipped a step there, so let me back it up and talk to you about how you get to the handy dandy Desmos matrix calculator, because it's not very handy dandy if you can't get there. All right, so go to desmos.com. And again, if you haven't already created an account so that you can save your work, I I don't want to be harsh and say I don't know what you're waiting for, but we're kind of getting there. You know, we're getting to the territory of like maybe you should do that, because saving your work and using that to make edits rather than reinvent the wheel as we go forward is going to become more and more important. Right. So math tools, drop down for the math tools. You can already see where we're going. We're going to matrix calculator, but you can see some other options there too. You know, we're familiar with the graphing calculator. If for whatever reason you just want to use 4 functions, there's a 4-function calculator. There's also a geometry tool for getting a sense of constructions and things like that. But we're just living mostly with the graphing calculator. But for today, we're going to go with the matrix calculator. All right. Now, this has some features that make it more advantageous than something like a TI calculator or even GeoGebra, which does also tackle determinants for us. The main feature is, well, I wouldn't even call it a feature. It's just really more like, you know, the selling point would be the fact that it looks the part. Right? It looks like exactly what we need. Oh, I want to put in a new matrix. Oh, well, voila, there we go. I would like it to be a 3x3 matrix. Well, okay, well, there, edit matrix A, number of rows. Oh, I can add to that. Number of columns, I can add to that too. All right. So then I just type in my values. It accepts them across, so left to right, top to bottom. So across each row, and then it works its way down. The 1. Oh. Then hit the right arrow. Because if you hit enter, it just locks it in like just happened there. So I just wanted to show you that. So 3, then right arrow, 5, right arrow, even though you want to go down, the next place available would be within the matrix, the next row. All right. Once you're in the last cell of the last row, then when you hit the right arrow again, it'll take you out of the matrix, but we don't need that. But 2, right arrow, -1, right arrow, 0, -3. It expands the format to account for any values that you put in there, which is nice. It doesn't have like that wraparound attribute like Excel does, where you just kind of, it truncates it and you know it's there, but you can't see it. All right, so then you can hit enter, locks it in. So now I have my matrix A. I want the determinant of matrix A. Okay. Det, DET, right next to RREF. All right. And which matrix? Matrix A. Oh, there's an A right there. Close parentheses. But you could see even before I closed the parentheses, it had already computed the answer for me. So we're looking at a -8. All right. So we got a triple scalar product of -8. Right. But we also want to be thinking about what that means. All right. So one of the activities that you did in the last tech assignment was to create a parallelepiped, right? And a parallelepiped is a 3-dimensional figure that's generated based off of the 3 consecutive or 3 adjacent vectors in space. All right, so there's a parallelepiped that exists in 3 space, and that's really just, again, the parallelogram projected out into the 3rd dimension. Right, so that's all that is. So when you think of it in that context, it's like, all right, well, that's good. Now, what does that mean? What does that tell us? Well, what we're getting from this is the volume of a parallelepiped whose corner is made up by the adjacent vectors u, v, and w, right? So this would be the volume with a corner made up of adjacent vectors U, V, and W. All right, so that's what that computation will give us, which is really nice, because if you think about the concept of creating, or at least I would just say, the thought of creating a parallelepiped by hand makes me nauseous. You know, it's along those lines where it's like, I don't want to do that. But to know that we can come up with the volume of that parallelepiped without actually having to come up with the diagram itself, even using something like GeoGebra, you know, just think about it. Like, there was a fair amount of steps in there. It was pretty lengthy. So we don't want to have to do that. The fact of the matter is we can come up with a volume without having to worry about that. Right? And so that's actually what a determinant gives you, depending on the dimensional value. So in this case, it's 3 dimensions, you know, the 3 components to our vectors, 3 vectors, we have 3 dimensions. And if it were 2 components to our vectors and there were only 2 of them, so a 2 by 2 square matrix, a determinant would give the area of the parallelogram into space. Right? So what we could actually do is just kind of hop back in time here for a second, go back to the previous page and take a look at PQ and QR, those 2 vectors that we've used to find the area. And let's just take a look and see what happens if we were to find the determinant. And I'll come back to this in a sec. But if we were to find, actually, it's a parallelogram in 3 space, so it's askew. But you know what I'll do? I'll just make up an example, because I don't want to have to work with that one and then risk screwing it up. But let me just kind of chuck it off on the bottom here. So we will go back in time. We will take our journey back in time, but I'm going to do it in a different way. So, and I'll take this as a typo. I'd like to have this example in there. So let's say we want to find the area. So this is page 33, I think. All you'd have to say is include new example of the parallelogram with adjacent vectors U equals 1, 2. I'll keep it relatively simple. And let's say V equals, I'll get something negative in there. Let's say -3, 4. All right, so I'll give you a quick sketch, because this one's in 2 space, so you're not going to have to watch me fumble around with technology and diagrams too much here. So I don't want to deprive you of any fumbling around, though, so I'll make sure I screw something up. And so 1, 2. So that's my U. My V is -3, 4. So from this, we can create a parallelogram. All right, so copy, paste. And remember, this is how we find a vector sum if we need to. All right, but we got a parallelogram out of it. And so this is UV. Now we know that if we were to find the cross product between U and V and then find that magnitude, that what we would end up with would be the area of this parallelogram. But let's find the determinant. All right, so I'll use techie notation for determinant. So determinant of U and V. All right, so that would be in the form of 1, 2. I'm using them as, I'm putting them in as row vectors just for consistency with the cross product technique. All right, just because I don't want to confuse people too much. All right, so what I can do is I can put a new matrix in. They're calling it B because I already used A. So I type in 1, 2, -3, 4, lock it in, and then determinant of matrix B. And I get a result of 10. Now, there's other ways that we could find this area. One way would be, if we went old school geometry, we could box it in a rectangle and subtract off little triangles. I mean, that would take forever. So we don't want to do it that way. But what we could do is use our magnitude of the cross product technique. That shortcut formula seems pretty nice. I mean, it allows us to not have to come up with an angle in between two vectors. So there's something there, so I would just need to know the magnitude of U, which is the square root of 1 squared. I'll write it out, 1 squared plus 2 squared. So rad 5. Magnitude of V. Three squared plus 4 squared. That makes a 3, 4, 5 right triangle. So, we're talking about 5 as a result here. And then U dot V. So the dot product of the two, -3 plus 8 is equal to 5. And you know what? As made up problems go, I don't think this could have got any nicer. In terms of the numbers, that's pretty solid. I'm just going to move that over, create a little more space. All right, so now it's just a matter of applying my handy dandy new formula. So the magnitude of U cross V, I guess I need the V in there, right? So rad 5 squared times 5 squared minus another 5 squared. Poor quality radical symbol. All right, so 5 times 25 is 125 minus another 25 is rad 100. Which gives you a result of 10. All right, so just by finding the determinant, we're able to make the determination of the area of that parallelogram without doing anything involving the magnitude of the vectors, the cross product of the vectors. All right, but there is a connection between the determinant and the magnitude of the cross product. The issue is, that's kind of skewing heavily into the worlds associated with linear algebra, and we run the risk of getting a little too sidetracked, but there's definitely value in there. All right, so that might be the subject of another video, just to show you where that connection is. Something about, like, maybe I'll talk a little bit more about the determinant and where it comes from, what it means, and how it connects to the magnitude of the cross product. right? So I'll take that as a typo. Somebody wants to send me a reminder to make a determinant video. That would be wonderful and appreciated. But for now, what I'm going to do is I'm just going to put a star on each of these problems here, because all they're asking you to do is apply this concept of finding the determinant in order to solve a couple of problems. I mean, number 11 being the more interesting of the two. All right, so I don't want to rob you of the joyful experience there. All right. So let me stop this video.